Hello everyone, today we will be solving Spectral Cup 2026 Round 1. Alright, problem number 1, a wonderful contest. As a person of competitions, you need to participate in a wonderful OI contest. And problems each with a full score of 100. Problem I has AI subtest, and each subtest has a score of 100 divided over AI. Okay, and it's a divisor of 100. Okay, that's good. Now, several contestants will participate in this contest. Suppose contestant solves X subtask of ith problem. Alright, so we just take sums of all subtasks. To prove that the contest is truly wonderful one, you have to check whether it is possible to achieve every integer from 0 to 100 and n. Oh, okay, I see what's going on. Formally have to determine whether the following statement holds. Okay, I see what's going on, so let's think about this. So first of all, we have quite a limited number of divisors of 100, and we definitely need a subtask with 100 problems. The reason is otherwise it's impossible to get all odd numbers, right? Because we need at least one. Like, it's impossible to get number 1 otherwise, right? So we definitely need that. Okay, now the question is, what do we do with other problems? Well, if we have 1 equal to 100, then we can just solve all other problems from 0 to 100, and so we can get all scores. So the only condition is that we have at least one problem with 100 subtasks. Alright, so let's just implement it. N, I'll just do bool answer. And if x equals 100, answer equals 1. And then we just output if answer, then we just print yes, otherwise we print no. Let's run out samples real quick, just to make sure we're not envisioning solutions. Yes, okay, seems correct. Let's just send it. Running. Right. Yeah, good job. First problem done. Okay, second problem. After learning about the autistic balance tree, Lijos, if that's how it's pronounced, encountered the following problem. You're given an array A consisting of n integers. You need to perform exactly m operations on A in order. Each operation consists of 2 steps. Specifically, in the ith operation, you are given an integer xi. You will first select a center index u and a non-negative length y, such that interval, okay, u minus y, u plus y lies entirely within 1, and okay. For each I swap elements, okay, so we just take that segment and we reverse it. Then mark the element at index xy. Mark the element at index xy. This element is already marked, nothing happens. Note that the marks are on elements, not on indices. Okay, so like if we swap them around, the mark stays. Okay, that means if an element is swapped with, oh yeah, they just said it. After performing all m operations, your task is to find the minimum possible sum of all elements that remain unmarked. We can just take a bunch of odd segments, reverse them, and then we have these like marks placed on elements. On indices. Okay, that's interesting. So in the perfect worlds, we would like to mark only the minimal elements, right? All minimal elements. But then it might not always be possible. So the first thing that I notice is that if we have this array, then it's never possible, like if you look at an even index, for example this one, okay, this is odd index, this is 1, right, because I'm from 0, it can never go to another like even position. If it's odd, it stays odd because every swap is on, every reverse operation is on odd length segments. So this is the first thing that we have to take a look at. Oh, it's actually possible. We can mark the same element over and over again. So now the thing is, we can always swap like whatever the index is. If you imagine the array, let's say we have xi here. Well, we can just take the minimum number on that parity of indices. So like if xi is odd, we can take the minimum of odd and just swap it here. Okay, that's good. And we don't need to output orders, do we? No, we only need to output the answer. So multitest, n, it's m. We output the array and we output the operations. Sorry, no, output input. Let's do that. So now let's just do a sum over all elements. We'll need that. So we'll need sum equals 0. We'll need minimum odd number, so minimum 0, because that has parity 0. It will be 2 to the power 9, and minimum odd number, 2 to the power 9. Let me just do sum plus equals AI. And then we can do, well, the thing about these marks is actually beneficial because we have negative numbers. It also makes sense to try to get rid of those. So it's a bit more complicated, but I think it should be easy. What we can do instead, we can just order all of them like this. We can do odds, evens. And then we can just do if I modulo 2, it's odd. So push it back here. Otherwise, it's even. So push it back here. Very nice. Now for every operation, we just need to check if it's parity. So we'll do bool pair equals xi modulo 2. Okay. And now we can do like this. We can do auto vector, I guess. Is that a good idea? Let's actually keep them like this in an array. Then we can do something like this. Will allow us to easily access the correct one. So now we can just do here, we can do VC of I modulo 2 pushback. Nice. So now we just take the minimum number and we also need some kind of position. So we'll do pos 2 will equal to 0, 0 first. So we take, first of all, if position, the parity is already greater or equal to vector size, it means that we cannot do anything, we just continue. Otherwise, we can do something. We just check the elements. We do if element at that position, if it's less than 0, it means that it's always beneficial for us to get rid of this. So we'll do sum minus equals element at that position. And then we also increase that position, so we do plus plus here. Otherwise, it's only if position is equal to 0 that we have first to remove it, right? Otherwise, we don't have to remove it. So we'll do the same. So we'll do, it's either if it's less than 0 or we haven't removed any element yet. So we do that, and in the end we get this. Okay, and then we just output the sum, and that should be it. Let's run out samples. I actually got a error. What did I do wrong here? That's interesting. Oh, yeah, my bad. We need to do the parity here. And the parity here. Nice. That should be enough. Let's run it. The answer is not correct. Do we need to find the maximum? Oh, we need to find the minimum. Oh, well, my bad then. And I forgot to sort them, so we'll do sort. Because we want to start with the largest one, I will do it like this. I will do r begin, vector 0, r end. So this will sort them in a descending order. That's good, and we do if it's greater than 0 or if we haven't moved anyone yet. That's good, just forgot brackets here because, okay. Now we get 6. Well, the second one is a bit too small, isn't it? So what's going on here? We only get 6s. Well, 6 is here. Oh, the issue here is that, of course, our index is supposed to go from 0, not from 1. And now we get correct answers. Yeah, so let's just send it. Also, let's not forget about the fast thing, because I don't know, maybe it's going to be too slow. Send it, and we should get the second problem too. Once in the queue, let's actually start reading problem C. Okay, you're given an array with odd length n consisting of positive integers. You are required to partition the sequence into several subarrays with odd length at the same median. Oh, that's interesting. Your task is to find the maximum number of subarrays. Find a strictly increasing sequence k of length p plus 1, where k1 equals 1, blah, blah, blah. Alright, so we want the medians, like the median element, to be the same. Alright, and we solve problem B. Okay, so that's actually quite interesting. And n is up to 5,000, and we know that n squared is up to 5,000 squared. Okay, let's think about what has to happen so that this answer like maximum possible. It's n, right? So for that, every single element has to be separate, so they have to be all equal. That's like an edge case. Now, I know that answer is bounded by maximum counts. What I mean by that, it's like an element that appears the most amount of times. So if we fix some element, let's say x, right, we can mark all the x's, and we can mark elements larger than it as 1 and smaller than it than -1. So now I have to have some array, some indices. So if this is, we need to like split into segments, each of them should contain x, and the sum on every segment should be 0. So that's interesting. So the number of elements larger and smaller should be exactly the same. So can we do some kind of dp here? We can do dp I sum, and we can either go to s plus a of I, which means we get this array, and if, oh, I also need to keep the number of x's. Oh, this might get a little tricky. Well, I could for every segment, like the issue is this solution will work, but it might be too slow because we need to do it for every value. But we might do like for every segment, every odd segment, we can just calculate the median. And then we can create this sort of like graph where we only have segments which are good. And now we just need to find like a longest path. Well, it's not exactly what you can do with the graph, but I'm pretty sure I can do this with dp. Let me think about this. It's just that in every position I, it's quite easy. Okay, so let's do that. The only difficult part remaining is that we need to somehow calculate median really fast for every segment. So let me think about how we can do that. I can do like an n squared log solution with parallel bin search, but I think it's too slow. There's like, it's an overkill. There's no reason to do that. So let me think about a better way to do it. Well, I know if I have some array and some median, if I add one element, well, I cannot add one element because it has to be odd. So if I add two elements, how far can the median go? Either both of them are larger, in which case it will move one step to the right, or they're both lower, in which case it will go one step left. Or they can also be lower and greater, in which case median will stay the same. So really, it will move only once when you add elements. So if I start with some position L, I can go R from L to n-1, and I can just move this boundary, and this will be O of n. So I just do that for every segment, and that's gonna work. Very nice, let's implement this real fast. So first we have multi-tests, and then we need to implement a solve function. Now we only input n and the array, I'll call it dat, as in data. Let's read everything. Now we need to do the thing where I calculate all the medians. So it should be quite easy. I think I'll just do like a vector. I'll have const max n 5005, and for every position it will know, it'll be like the next position and the value, right? Although it'll make sense more to sort them by value, so I think I'll make it like max n, and this will be like for every value, right? Elements up to 10 to the power 9, but it's not scary, we can just compress them, something like that. Alright, this is our graph. Now let's actually calculate it. So I'll go for every boundary L. Well, I don't need every boundary, I'll only need even ones, because otherwise we'll have... No, actually I do need those. Oh, let me think. Yeah, I do need those. I don't need every boundary, because you never know. Alright, so initially what I need... Oh shit, I think I need to keep them in some sort of like a set. This is gonna suck. Can I use some kind of a linked list for that? Although this might be an overkill. So my problem is I just have values, like an array of values, and I just want to insert an element somewhere. And for that I need to take the previous one and the next one. I need to like join them together. Yeah, so we want such an element that if we look at the count array, some on the left and right. Oh yeah, it's like the thing that we had, the formula that we had, like this is A, K, this is B. We just want like length divided by 2 to be greater or equal to A and lower than A plus K. and if it's not that, we just move up. That sounds okay, but I mean, it still might be a bit too slow. Like now, if you add 2 elements, you need to go up, but then if you add 2 elements here, you might need to go down, and it might be really, really slow. Come on, this shouldn't be that difficult. We just want to find medians on like a bunch of segments. It should be so easy. Come on, this should be really easy. Like I have a set of numbers, and for every each one of them, I just need to know the next one. And at some point, we are adding numbers. Could I do that from the back, actually? Because removing numbers is quite easy. Let's think about this. Well, it does require sorting, but sorting can be actually done here in O of n because we have really low numbers. I mean, they're not low, but we can compress them to be low. This took us quite more time than I would hope it did, but, well, what can you do? Still glad that we got the solution. I'm pretty sure that it's the correct solution. So let me create a vector VC. I'll just push everything inside of it. We'll do that to compress all the coordinates. It will make our life much simpler. Not coordinates, but values, my bad. Then we'll just go through all values. So we'll first do, we can do it like this. T size, and we can do index equals 0. Then here we do if I, and VC of I minus 1 equals VCI. We just continue. Otherwise, we do map of this value equals index plus plus. So now we can just go over all indices, all values, and say that data of that index equal to index. And we need to only output the answer, so we don't care about that. Equals to map data. Okay. So now we have all the values compressed. So now we can do O1 and sort. Let's create the array. We'll set all the medians. So we'll go L from 0 to n. We'll get all of the numbers sorted, so I'll create a count array of size n. Okay, so these are the counts. Then we'll go I from L to n, and then we'll insert counts I plus plus. No, sorry, counts of data I plus plus. So this will give us the sorted array. And now I also need to store for every guy. I need to store the next guy and the previous guy. So we will do int, so vector int r, like the guy on the right. This will be n0, n minus 1, and I'll do the same l, n minus 1. Okay, now just go through all values one by one. For every value, iterate as many times as we have it. And what do we do now? You can just keep like the previous value, I guess. Previous value is minus 1. For every guy, we'll just say that L of I, it's like the value, equals to... Oh, actually, here we need to be careful. Let's actually make it a big L. This will be big L too. Okay, so the left guy is the previous value, and previous value equals... Actually, let's do it here. Previous value equals priv, and previous equals if count. Now let's do it like this. If not count I, so if it's empty, we just skip it. Otherwise, we say li equals previous, and previous equals I. That's cool. Now we can do the same thing in the other direction. This way, we'll get all the left and right positions. So we can do previous equals n. Then we just go through all values from n minus 1 to 0. If it's empty, we skip it. Otherwise, we say that this is the next value and so on. Okay, so we have all of those. Now I just need to keep the medium position. So I'll call it pause. And we need to calculate it. It should be relatively easy. I just need the current counts. And I just need to know how much we have on the left and how much we have on the right. So we'll do sum L equals to 0 because we'll start at 0. Sum right equals to going to be, what is it? I think it's n minus L, so a number of elements. And minus counts at 0. Yep. So now we can do while So we can do mid, it's equal to n minus l, so number of elements, divided by 2. And we can do while middle is less than sum on the left, we need to move the position to the right, if that makes sense. Yeah. So the way we're gonna do that is do pause plus plus, and now we're going to do, first we do sum L plus equals counts at that position, because now it will be part of the left thing. And then we add it, and then we do sum R minus equal count at that position. Alright, now it should be good. So we find the medium, and now we just go R's from n minus 1 to L. Right, and now we do if. Now, how do we do this now? We can first set median of L to R equals pause. Right, this is the value. And now we need to remove the next guy. First we do int x equals data at that position, so the element. Then we do if count, we do count x minus minus, and then we do if count x equals 0, we need to merge it. So we'll do previous L equals L of that guy, previous right equals right of that guy. And then we do if PL is not minus 1, we do R of PL equals to PR. We do if PR not equals minus 1, we do L of PR equals PL. So we like merge them together. That's very good. And now we need to do the same thing here. So we do while. I mean, in practice it will not be a while, it will just be like a single if, but I still want to do that. So now we just need to check if x was greater than position, we'll do sum L, sum R minus minus, and otherwise if it was strictly less than our position, we'll do sum L minus minus. So now we do this, it's us moving to the right, and here instead of doing pause plus plus, we'll do pause equals R of pause. And we'll do the similar thing, but when we need to go to the left, so we'll do while mid plus while mid is strictly greater or equal to sum L plus count at position. So this means that median is lower. We'll remove that guy. And I think this is what we do, right? So we first say that this guy is no longer part of, no wait, this is wrong. I think we first say that this guy is not part of the L thing, R thing, and now it should not be part of L thing. Okay, hopefully that makes sense. We just move in that pointer and it should be of 1. And in the end, yeah, we should get all of the median positions. That's very good. Now we can finally do some DP. We actually don't need a graph, as I said before. We can just do a DP. So we will set all of the values of this DP some comically small value, right? So I'll just say DP ij equals minus like a billion or something. And then we can actually set what do we set actually? I think we just go over all values from 0 to n, and we set dp of 0i, like for that value, is equal to 0. And now we can do for every position I, we go to another position, which will be I plus, from I plus 1 to n. And then we need to do the check. We update dp of j, and the value is with value of, let's actually do it like this. Median is equal to, it's from I to j minus 1 if I'm not mistaken, yeah. Also we do it only if j minus I modulo 2 equals 1. Otherwise we continue. So we do the median and we update that dp value with dp I m plus 1. And in the end, answer equals to, it's at least 1. And then we just do factor for every value and update answer with dp of ni. And then it should be good. So I'm not sure it works as is right now, so I think I should just debug it. Oh, it's because this. I'm actually forcing myself to make only the even moves. What's going on? Okay, now it works. Okay, hopefully it will actually be the full solution. If it's not, I might get a little sad. Okay, so this is 3, that's correct. This should be 3, that's correct. This should be 9, that's correct. Let's actually do this. Let's run all of the guys. Let me run it on the samples to see that they work. So copy this stuff with input, output. And we got the answer 33911311355. That looks correct. Let's send it. And even though it was a big delay, I think it should still be the solution to this problem. Hi everyone, this is me from the future. As it turns out, there's a much simpler way to solve this problem. What you need to realize is that if we have this entire array and we have some median element, let's call it x, well, we know the formula that it needs to satisfy for it to work. If we count all elements less than it and call them a, number of elements equal to it and call them k, and number of elements larger than this, call it b, it needs to satisfy two conditions. First one is that a plus k has to be greater than b, and other one is b plus k has to be greater than a. It's kind of trivial, it's similar to what I had, it's just more clear to see how this one works. So k has to be like in the middle. And now you can see why x is the only possible median for all segments. This is because if we imagine we have some other value y, which is not a median, and we split array into a bunch of segments where this element is a median, now each segment, for that value to be a median, needs to satisfy the same formula. So it must have some ai, ki, and bi, and we know that for every I, ai plus ki is greater than bi, and bi plus ki needs to be greater than ai. And now here's the cool part. Because it works on every segment, we can actually sum all of these values together, and this means that it also works for the full segment, for the full array. Which means that it's a contradiction. Y has to be a median. With that observation, this problem practically becomes trivial. You just need to do the same DP that I had, but now you don't actually need the first argument, because we know the value that will be median on every segment. This greatly simplifies this problem, because now it means that we don't need to calculate median for every segment. So this is why it took me so long, but I guess it works. You know, sometimes you take more time than you expected today, but still, I mean, I think we solved it. While it's testing, I see there's a little bit of Q going on, so I will actually start to think about problem D. So the problem D was that we have some array A and we have some permutation P, and for every inversion, the value is the sum of all values in between from A. And the beauty of permutation is the sum of the values of all of its inversions. And what we need to do is find a permutation which for the given array A give us the maximum beauty, the maximum value. Okay, we did solve C, that's pretty good. Let's see where we are. Actually, not bad. We are doing quite well. Alright, so let's think about this function a little bit more. So let's just, for simplicity, say that AI is equal 1, right? It's like a subtask. All of them are equal. So if I have some permutation, let's say 2, 3, 1, I need all of the inversions. So it's when the value on the right is lower. Okay, so the inversions here are this and this. And what does this inversion really mean? An inversion permutation is a pair of indices. Okay, so it's just a pair of indices. Okay, so we will get some, like from this we'll get 1, and from this we'll get 2. And if we look at actual values, let's imagine these are values A. This one, from 2 to 3, will give us this value. And this one will give us these two values. Okay, and we need to create a maximum. Alright, so first of all, if all AIs are equal to 1, we know the answer is just the unsorted array, like when it's sorted in descending order, because then every pair will be an inversion. And actually I don't know what is the total cost. I wanted to say that it's n squared divided by 2, something like that, but it's actually not. It's the length between them. Wait, what? Isn't it just optimal to make their... Wait, what? That is so stupid. Oh, the values might be negative, that's it. Because I thought, I mean, can't you just make the array unsorted? Okay, so now we have negative values. This is interesting because if a value is negative, it means that we actually want 0 inversions. 0 inversions, okay. That's now getting interesting. Okay, well, what if we look at a singular inversion then? Like every single inversion. And we ask ourselves, is it positive or negative? Like, and this means, do we want to have it or not? So we would like to only have inversions where the value is non-negative, or it's positive. It doesn't really make a difference. But the thing is, it might not be possible, right? Like, if I have an inversion from I to j, and I have an inversion from j to k, is it possible for me to not have an inversion from I to k? Because that means I know that p of I is greater than p of j, and it's greater than p of k. So if I'm going to choose these two to have an inversion, and these two to have an inversion, well, this means I'll have this inversion as well. I just want to solve this problem, and I think I cannot finish the contest, unfortunately, because I have to go early, like 30 minutes earlier. But still, hopefully we can at least finish this one. So let's just think about adding the value to the start, not to the end. So I have some inversions which are all optimal. I know this is like the maximum thing. So now if I take this guy and I want him to get all of the positive inversions, when I insert him, what does this mean to society? Is it something to do with prefix sums? Because I just thought about this. If I have two prefix sums and I know this one is A, this one is B, well, I know that it's positive if A is greater than B. Wait a second, I think I just solved it. Let's look at the sample again. So what was it? So I just set this one to 1, this one to 2, this one to 3, 4, 5, and this one to 6. It's not exactly what they have, but it might as well be. Oh, it is exactly. Yeah, okay, we just solved it. It's so clever. Oh my god. It's so simple. Okay, so if you didn't understand what I did here, it's actually quite genius. So the theoretically possible, like the best solution, just imagine that. Alright? And what inversions would you like to have? Well, obviously all of the ones that have the value greater or equal to 0, right? But the problem that we even encountered before is that it's actually quite difficult to build it, like we don't actually know if we have it or not. But what you can do, it turns out, you can, because what is the value of inversion? It's sum of all values in between, like the right one is exclusive. So this means that it's actually prefix value of the one on the right minus prefix value of the one on the left. And what this means is that I want all pairs that have the prefix value on the right is greater than the one on the left. I want all of them to have an inversion. How you can do that? Well, you just sort all of the prefix values and you just reverse it and you set all those guys. Hopefully that makes sense. That's probably not the best explanation I ever gave, but well, what can we do? So I'll keep the sum. I think I should keep it as long because they have big values. So I will do prefix of I equals to sum and the index. I want to remember the index because I want to, of course, restore the answer. Sum plus equals data of I. Now we sort all the prefixes. Now I want the largest one to have the smallest value. So I do answer equals n. I go from the largest one at position n minus 1. I'll take its position, j, which is prefix I dot second. And then I just set, you can do like val equals 1. I just say answer at j equals val plus plus. And then just output it. So let's run this. Oh, I run it on the test from the file. Okay, 7. Oops, I forgot to call the solve function. Happens to the best of us. Copy 1 1 2 1 3 2 1 1 2 3 4 3 4 1 5 2. Now this one is tricky because actually I have the exact same answer as they do. Yeah. Okay, sounds good. So I think that's it. It's actually quite a lot simpler than C, I would say. Definitely. Like, the implementation is just so much easier. You just need to see this like mathematical fact, but after that it's just so ridiculously easy. Like, you could solve it anything. Okay, while that's testing, let's actually open problem E and try to solve that one. Problem E, seek the truth. This is an interactive problem. I like those quite a lot. There are two hidden integers k and c, such that k is from 1 to 3 and c is from 1 to 2 to the power n minus 1, and it cannot be 0. Before any interaction, you need to tell jury the non-negative integer a non-negative integer a. The grader will then use a as the initial element in the set, that is, initially s equals a. Next, you can make at most n plus 3 queries of the following two types. Select an integer x, okay, in that range, and the jury will insert f of x into s and respond with the size of s. Select an integer y from the same range, and jury will respond with the number of integers z, such that z is in s and z is greater or equal to y. So we can like take number of elements greater or equal. Definition of f of x is as follows. If k1 is bitwise AND, if it's 2 it's bitwise OR, and if it's 3 it's bitwise XOR. So actually you don't know the operation. This is crazy. This is very interesting. So we don't know that. And what is the C value? The C value is the one that I don't know actually. Your task is to determine the value of K and C using the most n plus 3 interactions. Wow. Okay, let's think about this. So first let's imagine we actually know, let's say that we know that K is equal to 1. How can we find C in n operations? So if I know that it's somehow somebody told me that K is equal to 1 and we have bitwise AND, what does it give us? How do we find C? Oh, it's actually quite easy. Since I know that it's AND, I can simply put a value with all bits equal to 1. So this is like 2 to the power n minus 1. And then I just do bin search. For that I use exactly n queries, because I can use the second type operation. First operation of insert f of x, and I'll say that x is 2 to the power n minus 1. So I will get x and c, and because x has every bit equal to 1, I will actually insert c. So I can do 60 operations, n operations, to find the actual value. And how many operations is that? If I already know that this is k equals 1, this will be one operation to insert the f of x, plus 60, my bad, plus how many, plus n operations to find the actual value. Okay, so we can do that, and I think we can do the same with XOR and OR, but the only problem is that we actually don't know this k. So what can we do about it? Well, I can try inserting 0 and 2 to the power n minus 1. Let's imagine XOR is not a possibility, it's either AND or OR. So I can ask about that, and now I will start with a equals 0 just for simplicity. If I know that the size, okay, so if it's AND, both of these values will be, this will be 0, I have already 1 0, and this will be C, right? And C is never a 0, so that's important. So then I will have two different elements. If it's an OR, I will get C, I will get 2 to the power n minus 1, and I will get a 0, so this will have 3 elements. So actually, if I just do 2 operations, I can, in fact, check whether k is 1 or a 2. This is just 2 operations. And then I just do n operations to actually find the value. Well, what do we do with XOR? Because XOR is quite a bit more complicated. If it's XOR, then what values will we have? We will have 0, we will have C, and we will have 2 to the power, like we'll have C inverted. Let's just call it that. So we'll just have inverse of C. Now, how can we differentiate between them? So the other case where we could get that, like 3 different values, was, I think it was OR. So this is XOR, and this will be OR. So if it's OR, it's 0, C, 2 to the power n minus 1. Okay? So how do we differentiate between those values? I mean, I can do one extra query in that case. I can just check y equals 2 to the power n. Because we know that C is not 0, this value can only be, it cannot be 0. So I think that's actually it. I know K, and I can just do a bin search after that. Okay, I have half an hour till my lesson starts, so let's hope we got it right. So okay, let's do one final one. If I had a 0 and I insert another f of 0, so what are the possibilities? It will either be 0 if it's AND, it will be C if it's XOR, and it will be C if it's OR. So I know for a fact that if the size is 2, it's definitely AND. Now let's say the size is not 2, so I have 0 and C. I need to differentiate between OR and XOR. How would you do that? Okay, I cannot find the value itself, right? I mean, I know that now it's just the maximum value, so I can find it in AND operations. Now I have this. So if I know C, if I know that it's 2 to the power n minus 1, it's an edge case, I just need to differentiate between this and OR. So this one will have 0, C. I just need to differentiate between the two. How do we do that? I think probably just add in something like a 1. Yeah, this will do it. Then let's say it's not that value. So let's say it's some value C, which is less than 2 to the power n minus 1. Can I just insert that value and see what I get? No, wait, I actually can't. No, I can't. But I can insert 2 to the power n minus 1. And since I know it's not 0, I know that if it's XOR, it cannot become that value. Okay, I think I got it. So let's first create this function. So we have select an integer, the jury will blah blah blah. So I'll do inline void add. And this means that I want to add some value x. So print I, x, and handle. That's it. And we'll have inline ll count. Right? So this is count for some y. We'll output question y and handle, and then we'll just input the result and return it. And this is the answer. Okay. Let's do void solve. Okay, so I input this value n. I'll output 0 and handle. Now it's time to do actual stuff. So I'll first do. Oh, I don't know the size of this set. Oh, that's the thing. Oh, they will know. They will return us the size. Okay, my bad. Okay, so let's do size equals add 0. So I know if size equals 1 still, only possibility is if this is an AND. So I'll do inline ll find maximum for some given n. So I'll do, I know k is equal to 1 and c is equal to find the maximum. So then I just output. So I'll have inline void answer for n. What do I need to output? K and c. C. Alright, and I think I should just, I don't need to return, so I'll just do answer for K and C and then return. Okay, otherwise I know the size is 2, so it's either XOR or well, that's what you get. Okay, so how do we distinguish between them? I know that C equals find maximum. So I know C now. And I just need to determine whether it was an XOR or a 1. So if c is equal to 2 to the power n minus 1, this is like an edge case. In this case, I just do size equals add like a 1, I guess. Yeah, add like a 1. And I would do if size is still equal to 2. I know the k. It's okay. I know the k is equal to 2. It's an OR. And otherwise, if size is equal to 3 now, it means the k is equal to 3. It's an XOR. And now I can just answer with k and c. And then return. Otherwise, I still have two operations to distinguish between them. So I guess I can just add 2 to the power n, and I can ask about it. And if it has that maximum value, it just means that it's an OR. And otherwise it means that it's an XOR. And I think that's it. Right? A bit confusing. We just need to implement this function real fast. I think we never ignore maximum, we just need to find the maximum. Should be quite trivial. So we'll do res equals 0, and then I'll just go for all bits from n minus 1 to 0. And then we'll do boolean has, which is equal to count all guys from res plus 1 to the power I. And if it has, then we know the res has a bit. And otherwise, it doesn't have the bit, so we just return res. I think that's literally it. It looks a lot more difficult on the surface. Like, once you understand how it works, it doesn't look that difficult. Okay, so let's check it. I think it works. Let's just sand it. Unfortunately, like, the contest is still running. We still have 45 minutes, but unfortunately I only have 15 because I have to go and actually do a lesson. But until that happens, let's actually read problem F. It has quite a long statement, and it's called building tree. X bar has an undirected graph with n vertices and m edges. The ith edge connects vertices ui and vi and has weight. Okay, so we have a weighted graph with n vertices and m edges. For every path, let the weights of the edges in it form a set S. Then the length of this path is defined as max of that S. Okay. Max denotes the minimum excluded of the collection. And distance denotes the minimum path length among all paths standing at u and ending at v. Oh, that's interesting. Now, X bar wants to construct a new graph with q vertices. In the new graph, the color of the ith vertex is C of I. Okay? Initially, there are no edges in this graph. If X bar adds an edge connecting the vertex u and vertex v, it will cause distance of cu, cv time. If vertex cu and vertex cv are not connected in the given graph, X bar cannot add an edge connecting vertex u and vertex v in the new graph. Determine the minimum amount of time X bar needs to span to make the new graph connected. Ooh. Okay, we did solve E. That's very good. So we have some graph, some weighted edges. Are they bidirectional or not? No, it's undirected graph. So something like that. So the length of a certain path, let's say I have this path, the length of this path is the max, so the minimum excluded value. So in this case it's going to be E1 because we have a 0, we have a 2 or a 3, but we don't have a 1, so the answer is 1. In this case it would be a 2 because we have a 0, a 1, a 3, but we don't have a 2. And the distance between two nodes, say A and B, is the minimum among all paths. So it's the minimum value of a path, minimum cost of a path, for all paths that go from A to B. I'd assume without any loops. Now we want to create a new graph with q vertices. In new graph, the color of I vertex is Ci. If X bar adds an edge connecting vertex u and v, it will cause distance of that thing. So if I say that I have some graph and I'm creating a new graph, let's say the vertex numbers are 0, 1, 2, 3. So let's say I have a new graph, and the colors here are actually the vertices. So it might be like 1, 1, 2, 0. So if I want to add this edge, the cost of this edge will be the distance between these two values. So in this case, like, I don't know what the value is. We don't have edge values, but that's what the cost is. If Expert adds an edge, if vertex CU and vertex CV are not connected in the given graph, Expert cannot add an edge, and we need to spend least amount of time making the graph connected. Okay, I think I understand the problem statement, but the issue is it's quite complicated, and I will probably not solve it with 6 minutes on the clock. So I think as for participation phase, that's it, and I will see everybody at Upsolving stage. Alright, welcome back everyone. Now we're actually upsolving. So I wanted to upsolve problem F because they didn't have enough time. Let me actually start the timer, shall we? I should have started now. Alright, so I vaguely remember this problem. So the idea here was that we have some kind of graph. Every edge has some weight on it. And we define distance between two nodes as max of all edges. It's like, I think is it the minimum? Let me check. Oh yeah. So because there can be multiple paths between two nodes, the value of a path, so the cost of a path, let's call it P, it's max of all values on that path. Right? It's like a max of all edges on that path. And the distance between two nodes is the minimum among all paths that go from A to B. Now, what is not clear for me is that, does the path have to be simple or not? So can I have some loops and other stuff? For every path, let the weights of the edges in it form a set S, and then the length of this path defined as max of S. Alright? The minimum path length among all paths starting and ending at V. I mean, they never said that the path has to be simple. The reason why that is important is because if you imagine we have some kind of graph and we have edge weight 0, 1, and 2. Now, I'm actually thinking about this. Oh no, wait a second. Oh yeah, we want to do minimum. I forgot for some reason. I thought that we wanted to do maximum. In this case, it would matter because it would mean that distances between all nodes in single component are the same. That's actually not so clear. That's an interesting function. And the problem is, when we had the graph, we actually wanted to construct a new graph where each node corresponds to some other node in this graph, and they can, like, two nodes can correspond to the same one. And if you want to add an edge, you need to check what nodes these two values correspond to and take the distance between them. And this will be the edge cost. And the task is to find minimum spanning tree. I mean, like the minimum cost to connect all of these nodes. Which is weird on its own, but let's not think about this too much. Let's just think how we can find the distance for now. Because even that is not so clear. If we have some graph and we want to find this distance function, which is really, really interesting. So let's think when distance is 0. Well, it's 0 if 0 is not present, if there exists a path between U and V which doesn't contain a 0. So it might contain a bunch of values like 2, blah, 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 but it doesn't contain a 0. So that's immediately interesting. And this means that if we had some graph, so first of all, that's actually quite interesting. Yeah, let me formulate what I want to say. Oops. What I'm trying to say is that if we have some kind of graph, it's like complicated, right? It's not a tree, it's like a graph. And we want to find all distances which are equal to 0, right? It's a minimum possible value. So it's like the best value. So let's find all that are equal to this value. So the thing is, this means that we need to effectively remove all edges with weight 0. right? Because we cannot visit them. If you visit any edge of weight 0, your max will be at least 1. So this is not what we want. So we want all paths that do not visit those, so we can just cut them off. And when you cut them off, we'll have like a bunch of connected components. And these connected components mean that everything inside of them, every path inside of them, has distance equal to 0. And now we can kind of continue this process, by the way. Like if we now ask, okay, among the remaining paths, which of them have weight 1, distance exactly 1? Well, these are those that don't contain a 1 but contain a 0. So for example, a path between these two nodes might contain a 1 or 2. And this is interesting. Let me think about this. Well, what you would like to do when you get in this situation, well, we can say that every node in the component has distance 0, every pair of nodes. You would like to compress them to like a single node, and then find some new edges, and like continue this, something like that. I don't remember what it's called, it's a condensed graph, something like this. But, in this case it's not so easy because the distances between components are not really clear. Now we need to not forget about the base problem, which is we need to find the minimum spanning tree. So we might not really need to know distances between every pair of nodes, right? I mean, we cannot really calculate this because it's like n squared, I guess, but still. So what was the statement? So we had like a bunch of vertices. Well, first of all, if there are two vertices that have the same color, I don't know why they would allow that. I believe they do allow that, right? Yeah, they do, which is really weird. I don't know why they would. Like, okay, we can just combine them into a single one. So we can now imagine that we just have some subgraph or a graph. Only some nodes selected, like blue ones are not, like they're part of the original graph, but not the one that we want. Now we just need to find minimum spanning tree. Now, what's cool is that there's like a very simple algorithm to do it. I think the simplest one is Kruskal's. Idea is simple, you just find the minimum edge. You check if it connects, like initially all nodes are separate. You find the minimum edge and you see if it connects to different components, you use it. If it doesn't, you discard it and then you continue. Then it can be proven that if you go through all edges in increasing order of their weights, then you will get minimum spanning tree. I mean, in this case, we just need to, in this problem, we need to find minimum weight to connect all of the nodes into one component. And this is exactly what a minimum spanning tree does. So we know that, and we know that we can get a bunch of components which all have distance 0 inside of them. So this means it kind of translates to our graph, because it just means that we'll have a bunch of nodes now, and we need to connect those. So now the only question is we need to find the minimum distance between all of these components, right? This is what we want. So let's ask ourselves the question, which of them have distance 1? And this is actually quite tricky. Let me think about this. Because we know we have a bunch of edges with weight 0 between them. So the question, which of them have distance 1? Wait a second. Doesn't all of them have distance 1? Wait, am I missing something? Because we can just take, like, we know that there's like two components and they have some edge between them that is equal to 0. And we're trying to connect them together. Well, what if I just take these two nodes, like exact these two nodes, U and V, that have that edge, and just use that edge, right? Wait, am I tripping? Like, yeah. This entire component just means there's like a bunch of nodes which are all connected with cost of 0. So now if we want to connect two such components, it means that we just need to add any edge between them. And we know there is an edge like that, or do we actually? Oh. Actually, don't really know that because that's the thing. it's essentially, I don't know how to describe this. Like these two nodes can actually be blocked. And what I mean by block is that they do not appear in the original graph. And if they don't appear in that graph, it means that we cannot actually use them. Oh, so that's interesting. If I forget about these blue components and I'll just have a bunch of components which all have max inside of them, they don't have any 0 or 1 inside of them. So this means that if I connect any two of these with an edge equal to 0, I will get weight equals 1, right? Alright, what does this give me? Well, it does give me a bunch of edges that I can use of length m, because like I know there's only m edges, so I can just check each of them and see if it works, and if it does I can just add it into a crucible. But now the issue is, how do we do this for larger length, like 2, 3, 4 and so on? How do we do this, for example, for 2? We need to break every component apart that has no 0, 1 or 2 between them. Oh, I think I see what's going on. Yeah. So let's imagine we have this graph, like the one that we are building and connecting, and it already has some edges, but all of them have weight less equals some number k, right? So now let's see, I want to solve it. I want to find all edges that have weight. Let me remove this. All edges that have weight equal to k plus 1, right? So I want to add like the next layer. How you do that is you remove, in your original graph, you would remove all edges with weight from 0 to k plus 1 inclusive. Actually, is the k plus 1 exclusive? Yeah, it's k plus 1 inclusive, sorry. It will break my graph into several components. And now, oh crap. Oh, wait a second. I think I got something. I thought for a second that my solution didn't work, but I think it does. Well, let's think about this. Let's remove every edge in our graph, which is equal to exactly k plus 1. So it will break the graph into several components, and they will have like edges inside of them, right? Now what I know is that none of the edges are actually equal to k plus 1. Wait. I'm missing something. Oh yeah. What I said was correct. So I remove all edges that are equal to k plus 1. What this does is that if I take any path inside of the component, I know that the value can never be greater than k plus 1. Why? Because, well, these components have none of those edges inside of them. They don't have edges with weight k plus 1, right? So this means that max value can never have that k plus 1, right? So it cannot never be greater than k plus 1 because k plus 1 is always missing. Well, it might be smaller, but we don't really care about this. Why? Because we've already added all edges which are smaller. So if you get some kind of edge and we say, oh, it has weight k plus 1, but in reality it has something lower, well, we don't really care because we use that already. So this is actually quite interesting. So we can now go over every edge inside of the component and use it here and say that it has weight k plus 1. So what is the problem now? I feel like something clicked, but I just don't realize what changed. Because obviously we cannot check every edge in the initial graph. Oh wait, we don't need to check every edge. We just take which one of them are in the same components, right? And then we just merge them together. Right. Let me think about this. So I have a bunch of nodes here. Then I'll do that algorithm where I remove edges equal to some weight k. Well, I guess k plus 1 doesn't matter. I get some new components My question is, does it mean that I can merge all of them into a single node? That's what I'm trying to think about. Because if we can, it's actually really, really useful, but I'm not sure that we can. It might be slightly more tricky. The problem here is that there might be a situation like this, like we have a component in our graph, but it's actually broken into two separate components in this new graph, right? And my question is, does this break anything? Like if we compress the initial component to a single node, will it break? Alright, I think I need to better think what these components are. So if I have a graph and I remove all of the zero edges, what does this mean? Well, first of all, the graph has to be connected, right? I think if the graph is not connected, it's just not possible to do it. I mean, it might be disconnected, but the component which is disconnected, it cannot appear, like only one connected component can appear in the graph, in the output. So this means I can assume that the graph is connected. Right? Yeah, because if it's not, I can just print -1. Okay, so the graph is connected. What does this mean? Is that between every pair of this, there's like some way to connect them using zero edges, right? Oh, well, we don't know how they connect inside. This is so difficult. What's difficult is that we cannot really predictably split it. Like, I would like to do something like DSU here, but it doesn't really work trivially. It must be something different. Well, I guess we can do DSU with like what it's called. It's not called persistent, I think it's like... Yeah, I think it's called persistent DSU. And we can do that. And now we can check for any nodes if they're in the same component. This is good. But how do we actually make those merges fast? Like if I have a bunch of nodes in my graph, some of them are connected, some of them are not. How do I quickly know how much of them will get connected, or like which ones will get connected? This is the difficult part. Well, oh, is it that difficult though? Like if I know that these nodes are connected, like these two, this means that at some point they were in the same group in the DSU, right? This is how they got connected. Well, what does this mean? Is that... Oh, what does this mean though? It means that whenever I'm adding an edge in my DSU, I can look at two nodes that it represents, and I can join them together, can I? Yeah, that's the point. I can join them together. Wait, what? So it's really easy now, isn't it? Wait, am I missing something? Well, I guess it's that... Oh. No, wait, what? This is so interesting. Okay, well, I guess the only issue is that the edge itself might not appear in that graph. Oh yeah, that's the issue. But wait, we can just, for every component, check if it has some good node, like a node from the output graph. And if we check if two components have that node, we can just merge them together. But yeah, I think that's it. I think that's actually it. I think all I need to do, I need to keep a DSU. And every component just needs to know if it has a good node, and if it does, what number does it have? Let's call it X, I don't know. And we need to be able to add edges and remove edges. Well, of course, DSU cannot remove edges by default, but there's a technique, which I'll show in a second. It's called like persistent DSU, something like that. Oh no, I think the name is DSU with rollbacks. Right, so that's the idea. You cannot actually remove an edge from DSU, but you can do a rollback. So I can do that, and every time I add an edge in DSU, I take a look at these two nodes, I find if they both have a good node, and if they do, in the original graph, like not the original graph, sorry, the answer graph, I look at them in this answer graph, and I see if they're in different components, I connect them and I add the weight. Yeah, I think that's it, and it's quite easy actually. Well, is it easy though? Yeah, I mean, that's it, right? So let's just implement this. So what do we need? I mean, the last part that I'm not so sure about is, I know how this rollback DSU works. And if I look at some edge x, some edge with weight x, and I imagine time steps going from 0 to n, minus 1, I guess. This edge x will only be present in like the prefix and the suffix, but it will not be present in this exact spot. So that's the idea, that every edge exists on a prefix and a suffix. Well, I can do that. Oh yeah, and every time I'm in some position, it's very easy, yeah. Yeah, okay. Let's just implement this. First we have multi-tests, and we need to implement a solve function. Well, this problem is actually surprisingly easy once you realize how to find all edges, all pairs of nodes with a specific distance. It's actually not that difficult. So we get n, m, q. What is q? Oh, it's the number of new vertices in the new graph. Okay. Alright. So now we input the graph. So what do? We don't actually need the graph itself, we just need the edges. Well, I guess the graph is its edges. Sorry. But I think we only need edges, yeah. So I think I will do it like this. Weight is up to m. Well... how do we do this? Let's just do vector of pairs, call it edges. And we'll have maximum n. So this is just a list, a vector of all edges with a certain weight. That's what we want in this problem. This will be the simplest way to go about this. So it's input. So we got A, B, W. Now W is up to M. Alright, that's okay. So we can just do A minus minus B minus minus, and we can do edges for W, push back, AB. Okay, that's good. Now, what do we want next? We need to determine for every node if it's good or not. Alright, if like it appears in the output graph or it doesn't. Alright. So on the next line we input all the good nodes. And I think I also need to do V minus minus, yeah. Because they go from 1 to n. Okay, that's good. Now we just create DSU. Right, because what do we want? Yeah, we just create DSU. Let me think about this for a second, because we do want rollbacks. Alright, yeah. Just create DSU. We'll have a bunch of parents. These are sizes. And this is Boolean if it has a good node. Has good. Create a constructor. Just n. Do we want a constructor now? I actually don't think we want a constructor like that. We'll just want a void clear function. Or guess void build, which accepts n. We want to set all of the values. So we'll do p of I equals I, size equals 1, and has good I equals good I. Alright, then we can do combine function. Before that, let's do the lead function, that's what I call it. But I'm pretty sure there are other ways to call it. So we'll do if p of v equals v, we just return v. Now let's return p of v. Oh wait, we actually don't need the, what it's called. We don't want the, what is called, the condensation, something like that. You just want to return lead of p of v. Because when you do rollbacks, you don't want the condensation because it's of 1. Well, it's reverse Ackermann constant, but it's kind of 1. But it's only that, what is it called? Not approximately, but like, oh damn, I actually forgot the word. It's all of 1, only amortized. And because we're gonna be doing rollbacks, it's quite bad to do those. Alright, so we got that. Now let's do the combine function. A equals lead of A, B equals lead of B. If they are equal, we return false. Now we do if size of A is greater than size of B, we swap them. And we do parent of A equals B, size of B plus equals size of A, and has good A or equals has good of B. Alright? And we just return 1. Oh, it's not a function, it's an array. Okay, very nice. Now we do want some kind of stack with all changes. We can use pointers for that. Do we do pointers? Yeah, let's just do pointers. Although, let me think about this. We do have this has good. Let's actually make it an integer. It will make stuff simpler. You'll see why. Yeah, let's just do pair of pointers. And first one will be the pointer, and the next one will be the value. So we'll call it a stack. And here we want to do stack push pair of this and this, so all the previous values. So it's parent of A, size of B, and has good of B. That's why we change has good to boolean, because I don't think that it will work. Sorry, that's why we changed to integer, because I don't think it would work with boolean. It got confused because it will have like pointers pointing to the boolean, so I don't think it will work. Okay, we have that. We can also do get stack size, and we can do, let's make it inline, and we can do rollback. Here we just do while stack size is greater than the size. We do this pair, which is equal to stack.pop. That's actually stack.top and then stack.pop. Then we do, how do we do this? Value at this pointer equal to p second. I think that's how you do it. Alright, so these are all of the rollbacks. That looks good. Now, what do we need now? So I will actually have 2 DSUs, which is interesting. Yeah, I think both of them will just work. So we'll have DSU OG. Now let's just call it D1 for the original graph. And let's do this here. DSU D1 and D2. Alright? So we'll just do D1 build for N. And D2 build for N. Alright? Looks good. I think I do need a list of all good nodes though. So I'll call this array like C, I guess. Why not? We can also do C of I equals V. I think I do need this. Yeah, I don't know. I probably do. Alright, now let's actually do all of the edges. So I know that for every edge of every weight, I need to have it like on a prefix and on a suffix. And the best way to do it is with like a segment tree thing, I guess. So let's call it all the edges. Let's call it seg. And do inline void add edge. We'll accept an edge and an interval. And I'll do like an interval function. Inline void underscore add edge. So there's V, L, R, L, R. Now we do if this, then we just do seg pushback E. Oops, seg of V dot pushback E, and then just return if L is greater than L. Return. So we just do like a regular segment tree thing. Add edge E. Here. And in the right segment too. Let's make sure we don't make any blunders here. It's quite important. Okay, now let's just implement this. So we do add edge E. let me think about this. We do want some size thing. So we want M to be public actually. I mean, not public, we want it to be global. A reason for that is because we have multi-tests, so you can have a lot of tests with... Yeah, you can have like a lot of tests with low values of M, and if I don't account for that, we can have a really, really long execution time. Alright, let's go 1, from 0 to M, from L to R, and that's good. I think this looks alright. We might also need to clear, so let's do inline void builds. And this will just go to all of these values, and I'll just seg of I clear. So let's call it build. Now we go for every edge. So we go for every weight. And then we go for every edge. And we do add edge. We do if W, we add edge E from 0 to W minus 1. And if W plus 1 is less than or equal to M, to add edge from E to W plus 1 to M. Alright, looks fine. So we add all those edges, this should be M log N. And now we can do the actual thing. So we first need number of components. And I think this is why we needed this. So we can do component count, it will be 0. Then we do, if it's a new node, so if not good of V. If it's not good yet, we increase it. So this means we have a new one. Alright. Looks good to me. Oh, my phone is actually dying. Let me plug it in. Alright, so now I need the solve function here, but it's not really solve. I can call it, oh actually this shouldn't be inline. I can call it recursion, I guess, to have V. I think it's, it actually needs L and R also. So we do if L equals R. What does this mean? I don't think that actually means anything. That's what interesting. We need to add all of the edges, and then we need to roll back all of the edges. So actually I want this component count variable to also be global. This is where I'm going to change it. I probably could have passed it as an error value, but I don't know. We'll see. If we get bugs, we'll do that. So I'll go for every edge in seg of V. I want to add all of them. Well, first of all, I want to remember the size, so I'll do ds1 dot get. Why cannot I call it get st size? I might have a few errors here and there, but we'll fix them, so don't worry. So we have the size. Now we add all the edges. So how do we? It's ds1 combine E first, E second, right? Is that correct? Let me think about this. Yeah, we combine, and we want to check if we do combine. We want in ds2. Oh wait, it's actually more complicated than I thought. Let's do so that this combine returns the two good values. And I forgot that this actually has to be, if it's good, it has to be I, otherwise it's -1. And here we just do if has good B is not equal to -1, has good A equals to has good B. And how do we do this? Also, we can do, okay, in this case we just return -1, -1. Here we can just do result equals make pair, which will have has good A, has good B. Right, and then we just return this result. I think that's it. So now here what we can do, where is it? It's the rollback. Here we are. We can just do auto new edge. Now we do if new edge dot first equals -1 or new edge dot second equals -1, we just continue. Otherwise we do ds 2.combine. And if we do combine, we will say number of components count minus minus. Looks good. Then in the end we want to do the rollback, so we'll do rollback like this. And here we actually want if L is not equal to R, we actually want to go recursively down. So recursion V times 2 LM, recursion V times 2 plus 1, M plus 1 R. Alright, we did that. So now we just call this recursion here. Okay. And in the end, we need to check if number of components is not equal to 1. We can output -1, return. Otherwise, what does this mean? It means that we've actually found the solution. So what we need to do... Oh, wait a minute. We need to find like a minimum. Oh, yeah. Okay, I got it. I got scared for a second because I forgot that we need to actually find the weight of the minimum spanning tree. So let's do answer equals 0. Well, just answer. We'll set it to 0 here. And now, if we combine them, here, if we combine them, what is the cost that we're going to pay? The cost we're going to pay is the minimum time in which they become connected, which is L, I believe, right? Yeah, if that edge was somewhere on the left more, we would connect them sooner, in which case it would be in the same component and we wouldn't pay this. So L is truly the minimum weight that we are going to pay. And let me think clearly if it's an L or not. If it's exactly L, I think it is, yeah. So in the end, we just need to output the answer. There might be a few bugs here and there, but I think it should work relatively well. Alright, it seems to work, so let's just send it. Took me quite a while to implement this. I honestly haven't done DC with rollbacks in quite a while. And I mean, it's not that easy. The problem is not that easy, so it's expected that it will take me some time. Wrong answer on test 1. What did I do wrong? Oh, yeah, another stupid mistake. I also forgot to clear this array. So I need to do edges of I clear. Okay, I think now that should be it. Yes, it does work, so let's send it. And now hopefully we should get a proper result. Right, it's testing. I mean, I think it's going to get accepted, but maybe we like did something too slowly. But I think it should work. It's n logarithm squared. And it does pass, very nice, 1.2 seconds. And the time limit was 2.5 seconds. Very good. So with that, thanks everybody for watching, and I see you guys in other Olympiads. Let me know in the comments if you have any suggestions what I should solve next. And I see you in the next video. Bye.